Hello, my name is Jay Lim, and I'm a PhD student at Rutgers University with my advisor Santosh Nagarkate. Today I would like to share an exciting method for approximating elementary functions for 32-bit representations. All endeavors in science, from structural engineering to scientific simulation, use math libraries to approximate elementary functions. Unfortunately, mainstream math libraries do not produce correct results. So the goal of our work is to create approximations of elementary functions for 32-bit representations that produce correctly rounded results for all inputs. In the context of the RLibM project, we have been making a case for approximating the correctly rounded result rather than the real value of f of x. And once you do that, you can use linear programming to generate polynomial approximations. To make this idea applicable for 32-bit representations, we make three contributions. First, we generate a piecewise polynomial. We also use a program synthesis-inspired methodology to generate polynomial approximations using a handful of inputs. And we propose a methodology that handles various range reductions. The resulting approximation functions for 32-bit float and positive representations are fast and produce correct results. Now let me start out by first describing what correctly rounded result is. Consider a real number line here. 32-bit float can only represent finitely many values. And let's say natural log of x1 is this blue value, then you have to round this value to a 32-bit float value, which is the green v1 in our case. This green v1 is called the correctly rounded result. An approximation function that produces the correctly rounded results for all input is called the correctly rounded approximation function. In the RLibM project, we have been making a case for approximating the correctly rounded result to generate polynomial approximations. In contrast, all existing libraries have been trying to approximate the real value of f of x. The intuition of the RLibM project is that there is a range of values in the vicinity of the correctly rounded result, this gray box, where all values in this interval rounds to the correctly rounded result. We call this interval the rounding interval. So RLibM has been generating polynomial approximation functions by first computing the correctly rounded result of f of x for each input, and then identifying the rounding interval for each result. Each rounding interval defines a constraint on the output of the polynomial that we want to generate. Using these constraints, RLibM frames a problem of generating a polynomial as a linear programming problem and uses an LP solver to generate a polynomial. Now our question is, how do you make this work for 32-bit representations where there are 4 billion inputs? To make the RLibM idea applicable for 32-bit representations, we propose three techniques. First, instead of trying to generate a single polynomial for all inputs, we generate a piecewise polynomial by splitting the input domain into subdomains and generating a polynomial for each subdomain. To make sure that we can efficiently identify which polynomial to use for a given input, we split the input domain based on the bit pattern of the input, such that we can mask a few bits in the bit string and identify the correct polynomial. Second, each subdomain still may contain millions of inputs. LP solvers cannot feasibly handle millions of constraints. So we use the counterexample guided polynomial generation technique inspired by program synthesis. We first sample a small number of constraints and use just these constraints to generate a candidate polynomial. Then we check if our candidate polynomial satisfies all constraints in the subdomain, and if it does not, we identify those constraints and add them to our sample pool. Then we use the new sample of constraints to generate another candidate polynomial and repeat this process until the polynomial satisfies all constraints. Third, we propose a methodology that supports a variety of range reductions. For more details in our methodology, please read our paper. Using our approach, we generated several approximation functions for 32-bit float and 32-bit positive representations. All of our functions produce correctly rounded results for all inputs. But more importantly, our library is faster than mainstream math libraries that have been optimized for decades. Mainstream math libraries do not produce correctly rounded 32-bit results. To conclude, we make a case for approximating the correctly rounded results and use LP formulations to generate polynomials. To make these LP formulations feasible for 32 bits, we generate piecewise polynomial instead of a single polynomial. We use counterexample guided polynomial generation technique inspired from program synthesis, and we propose a methodology that supports various range reductions. Our resulting approximation functions for 32-bit float and 32-bit positive representations produce correctly rounded results and are faster than mainstream math libraries. Thank you very much, and please give our math library a try.